Okay, welcome back everybody. This is Unit 2, Part 2. We'll talk about pressure here. So we obviously have to begin with the question of what exactly is pressure. And we introduced this in class when we did the blow up a student activity. And we also talked about a barometer and how they work. But pressure can be defined like in a textbook. More of a textbook definition is force per unit area. But for this class, what we talked about it was more of getting you to think about it in terms of at the particle level what happens. And the idea would be that in a closed container that you have particles that are in constant random motion, and as those particles are moving around, whether in normal conditions or if we increase the temperature, each particle is colliding with the walls of the container. And so the more often we have collisions with the walls of the container, we have an increase in the overall pressure of the system. So if you remember back to putting your fellow students up on the desk, you blew into the straws, and as you added air particles inside the bag, the more particles there were, the more collisions there were with the walls of the inside of the trash bag, and that helped to raise your fellow student off of the desk, and it inflated the bag. The units of pressure that are used commonly are inches squared, meters squared, maybe even in the United States, pounds per square inch. But we can also talk about pressure with the particles in the air and how they exert pressure down, the force that they apply down on Earth or on a surface. And in that case, we talked about things like millimeters, mercury, torr, which was named in honor of the inventor of the first barometer, Torricelli. And we also then talked about pascals and kilopascals, okay, along with one of the more important units that we use because it's the SI unit for pressure measurement, and that's the atmosphere. So on the next slide, we'll take a look at the relationship between these units of pressure, and then we'll do a couple conversion problems. Okay, in terms of units of pressure, 1 atmosphere is equal to 760 millimeters mercury. Millimeter mercury and torr are equal to one another, so we can also say that 1 atmosphere is equal to 760 torr, and 1 atmosphere is equivalent to 101.3 kilopascals. So we can use these unit conversions, or these conversion factors, to convert from one unit of pressure to another. So for example, we'll do 1 or 2 problems here, and let me just mark it so everyone's on the same page. We'll go with a standard atmosphere, so let's say 1.5 atmospheres, and I'd like you to convert that to millimeters mercury. So if we use our factor label method, or what we've been calling dimensional analysis since we started, is if we need to cancel atmospheres, we need to have atmospheres on the bottom. Okay, so the first thing we do is we can write that in. We want to then, because we know that to cancel out, we want to convert to millimeters mercury. We can see right here that there's a direct relationship between atmospheres and millimeters mercury. So what we can do is we can plug in the 760 millimeters of mercury, which is equal to 1 atmosphere. And what that leaves us with are the units that we want which in this case are millimeters mercury. So we would take 1.5 times 760 divided by 1, and we would get our answer. Now, just for a little bit of extra review, the question you should ask yourself here is, how many significant figures should I have in my answer? So to try to identify the number of significant figures, what we want to do is we want to look here and say there are 2 sig figs, and we don't worry about sig figs in this part of the equation because this is a conversion factor, and we don't have to worry about conversion factors. So it's pretty easy. We look at our given, which has 2 sig figs, so our final answer in millimeters mercury should also have 2 significant figures. Okay, we'll do one more sample problem here just to make sure everyone is a little bit more comfortable. But what we're looking at is sometimes people don't like to go from torr to kilopascals. Even though there is a direct relationship, they feel more comfortable working from atmospheres. So if we're given a problem, and let's say we have 500 torr, and we want to convert that to kilopascals. If you need to do a multiple step problem, that's fine. Here's how we would set it up. In order to cancel torr, we have to put torr on the bottom. If it makes you comfortable to go to atmospheres, you can see up at the top here that direct relationship, atmospheres to torr. Let's just use those numbers. So what we have is 1 atmosphere will go on top, 760 torr on the bottom, and we can see here that our units will cancel. And then if that makes you feel better and you know the relationship between atmospheres and kilopascals, we set up our next step. Canceling atmospheres means that we have to put it on bottom. Kilopascals can go on top, and then we can see from right up here in our conversions that the relationship can be put in. It's 101.3 to 1, and what we're left with is, pardon me for just 1 second, what we're left with is right here, kilopascals is the unit, which is what we wanted. We can see all other units are canceled out. And so in order to solve this problem, we take 500 times 1 divided by 760 times 101.3 divided by 1, and we should end up with the correct answer. And then just to look back and talk about significant figures, what we see here is that our given actually only has 1 sig fig, and because this is a conversion factor and this is a conversion factor, we don't need to look at those. We would want our final answer to have 1 sig fig. Now, if the answer looks weird or you don't feel comfortable with just 1, keep it reasonable and don't put any more than 2 sig figs in your final answer. Lastly, on this part of the presentation, what we're going to talk about is what we did with after we talked about units of pressure, how pressure is related to different variables. And what we talked about in class and what you all did in the lab was what happens to pressure if we change temperature, if we change volume, or if we change the number of particles in the system. So this is what we referred to as we started to do these problems as our PVTN tables or our IFE tables. Okay, and when we say IFEs, what we're talking about is the fact that we would plug in the initial conditions, then we would talk about the final conditions where we ended up, and then we would use arrows to talk about the effect. Okay, so on the following slides, what we're going to do is we're going to talk about the relationships between pressure and those three variables, and then do a couple of example problems. The relationship between pressure and volume is an indirect relationship. As one goes up, the other goes down. So we say that P is proportional to 1 over V. If we were to draw the graph for this, it looks like this. Pressure versus volume. It does something along those lines. Okay, the second relationship we looked at was what happens to pressure when we change temperature. And this is a direct relationship. Pressure is directly proportional to temperature. And the graph for this would look like this. As we increase temperature, pressure goes up. Now, of course, with the way I've drawn it here, temperature must be on the Kelvin scale because it's going through 0. Okay, so this is pressure versus temperature on the absolute temperature scale. Okay, on the next slide, we will just do a little reminder of what pressure and temperature looks like when it's on the Celsius scale. So pressure and temperature when it's in degrees Celsius would look like this. And if you remember back to your lab, some of you got some really good data. If we were to extend our axes out and find out where this line crosses, this is where some of you got real close to minus 273 degrees. And minus 273 degrees Celsius is 0 Kelvin. So the reason why when we talk about pressure versus temperature graph and why it looks different is because if we move this up and we make the graph between pressure and temperature and it's Kelvin, it looks like that. So there is a difference in the way the graph looks, but you should be familiar and able to identify either graph, knowing that it could be off of the Celsius scale or off of Kelvin. Okay? And while we're on this, let's just go ahead and put this little equation up that Celsius plus 273 gives us our answer in Kelvin. And again, that's not degrees Kelvin, it's just in Kelvin. Our final relationship is talking about pressure and the number of particles. Again, this is a direct relationship and says that as we add particles to the system, that pressure will go up. Now, based on what you did with your blow up a student and what you did in your lab with the syringe and the vernier equipment, is that as you add more particles, that obviously is going to mean that there's more movement within the system, that particles are colliding into each other, they're moving, and they're colliding against the walls of the container more often. If they're colliding with the walls of the container more often, then that means that we're going to have an increase of pressure. Okay, so PVTN tables, the only one that's not a direct relationship is pressure and volume, and we must make sure that we convert all temperature measurements into Kelvin units. So on the next slide or two, we'll do a couple of example problems. Okay, our first problem here, we're going to try to do a fairly basic one with just a single math step to get us to our final answer. We'll go ahead and we'll start by setting up a PVTN table. and or an IFE, and we'll go initial, final, effect, P, V, T, and N. And again, if it depends on how comfortable you are with doing these problems, how much information you do or do not put in the tables. But just be reminded that we do award partial credit. The more work you show, the better. And it also is just a good visual to keep you on track. But if we say that there's an initial pressure of 1 atmosphere, and it's at a volume of 5 liters, the temperature will remain constant. We're not going to add any new particles or take away particles from the system. So what would happen to the pressure if the volume goes to 3 liters? Okay, so the volume has gone down, and because we know that pressure and volume have a relationship which is an inverse relationship, if volume is going down, then pressure must be going up. Okay, so the use of the arrows is really important. Again, it does depend on your comfort level, but it's very important. So let's walk through how you set up this equation. I'll use a different color here. We always start with our given, what we're trying to solve for, which in this case is atmospheres, pressure. So we start with 1 atm. Now if we expect pressure is going to increase, okay, we look right here, we say it's going to increase, so we want this number to get bigger. If we want it to get bigger, we need to multiply by a larger number on top. So we set this up and we say larger number on top, 5 liters, over our final volume, 3 liters. Our units will cancel. What we're left with is atmospheres. And so to solve the problem, we take 1 times 5 divided by 3, so 5/3, and I don't have a calculator on me, but you should be able to easily solve that to fill in your answer here in atmospheres. And what we're going to see is that the final pressure of this system will be higher than it was initially. Okay, and we'll move on to another problem now. A little bit more complicated, a multiple step problem. And for our final problem, we'll just solve for pressure again, but what we're going to do is we're going to work with multiple variables. So as I set up our next PBTN problem, we need to, let's say, keep the number of particles, so let's not mess with that. Okay, if we have an initial temperature of 270 Kelvin, and that's really important, so let me point that out. I've got to put this in Kelvin. Okay, so if you're given anything in degrees Celsius, you need to go ahead and make that fix immediately, and maybe even to help you put a little K up here. At 270 Kelvin, at a volume of 2 milliliters, a gas was exerting a pressure of 1.5 atmospheres. Okay, if the volume changes to 1 milliliter and the temperature actually goes down to 250 Kelvin, what will happen to our pressure? What will the final pressure of our system be? So what we need to do next is identify what's happening, what's the effect. Temperature went down, volume went down. we have to determine how each of these changing variables is going to impact the overall pressure of the system. Now, where students struggle here is they typically forget to put both relationships in the effect box for pressure. Okay, so if we think about our relationships, as volume goes down, we would expect pressure then to go up. Okay, and then if we look over here, temperature goes down. As temperature goes down, it means particles are moving slower. So what we would have would be the pressure would go down because of the temperature change. And so what we see then is we don't really know what to fully expect, because one variable we should see an increase, but the other variable we should see a decrease. Now, as long as we understand the relationships, there's no reason why we shouldn't feel confident that we can get the right answer. So, in setting this up, let me change colors here. Maybe that helps you follow along easier. We always start with our given, 1.5 atmospheres. The next step, it does not matter if you use the volume relationship or the temperature relationship first. We just need to make sure we get them. Because I wrote the volume first, I expect pressure to go up with volume. So I want the bigger number on top. Our units will cancel. And then because I expect the pressure to go down in regards to temperature, I need to put the smaller number on top. So 250 Kelvin over 270 Kelvin. I'm left with atmospheres for my unit, the only unit remaining. I should probably go ahead and use 2 sig figs. That would seem to be the most reasonable number because I have 2 here and here and here as well. So when I do my final calculation, I'm going to take 1.5 times 2 times 250 divided by 270, and I'm going to get an answer. Again, it's all about understanding the relationships and knowing how to fill in these IFE tables. So practice away, go back to your worksheets, and good luck.